Good morning, students. I hope you all are well and doing linear algebra comfortably. Till date, we have done vector space, vector subspace, linear combination, span and spanning sets. Okay. Now we'll look at the structure of vector space in depth. So let us continue. Let V be a vector space. As you know that if I write V be a vector space, then it is understood that V is a vector space over the field F. F may be a set of complex numbers or set of real numbers, whatever it is. So if I write V be a vector space, that means it is understood that the field is given, and here we assume the field is a set of real numbers. Let V1, V2, V3 up to Vn belongs to V. Also, suppose these are the vectors, members of set V, and let us suppose this is the set S. Then, if you can know that span S, that means sometimes it is written as span V1, V2, V3 up to Vn is a set of linear combination of the vectors that means this is C1 V1, C2 V2, Cn Vn, such that C1, C2 up to Cn, they are the scalars, and here the real numbers. So this is the definition of span S. So what is span S? This is a set of linear combinations of the vectors V1, V2, V3 up to Vn. This we have already done. Today we will prove that this span is a subspace of V. Okay. So this is just revision. Prove that is a subspace of V. Now you just recall the definition of subspace. Let W be a non-empty subset of vector space V. W is called subspace of V if it is closed with respect to addition as well as scalar multiplication, and these two operations are in vector space, that is V. So if alpha plus beta belongs to W, for all alpha beta belongs to this, and second one A alpha belongs to this, for all A belongs to F field, and for all alpha belongs to W. Any people know the alternative definition, that is A alpha plus B beta belongs to W, then W is a vector subspace. So you must remember the definition of this one. So here we apply this. So first we will prove that is this is non-empty. Okay, so see, span S. So let V1 V2 such that okay, now remember, this is the identity element because this is the vector space. So this is the identity of this one. Additive identity. Okay. Now therefore I write it as C1, C2, C3 up to is V1 plus V2 plus V3 Vn. This implies is a linear combination of V1, V2, V3 to Vn. This is the linear combination. Here C1, C2 up to Cn, these are the scalars, that is 0. Remember, it looks like 0, but remember this is the additive identity element. You people know that. So if this one is written in this particular format, because we know that S is this one, then span of S is C1 V1. These type of elements we have in this one, such that C1, C2 up to Cn belongs to R. This we have done. So if S is this one, then span S will have this type of members. That means linear combinations of V1, V2 up to Vn. Now we people know that this is the member of V, and this one can be rewritten like this one. So this is a linear combination of this one. That means this is the member of this. Therefore, belongs to span S. Therefore, span S is non-empty set. So first we have proved that this is non-empty set. Okay. So this part is done. Non-empty subset of this one. Now we will prove these two. So let's see. Let alpha beta belongs to span S. Which type of elements in span S? Linear combination of V1, V2 up to Vn. So therefore, alpha is C1 V1 plus C2 V2 Cn Vn, and beta is suppose D1 V1 D2 V2 Dn Vn. Therefore, alpha plus beta, you people know that is C1 plus D1 plus C2 plus D2 Cn plus Dn Vn. C1 and D1 both are scalars and sum of two scalars is again scalar. So let us suppose this scalar is, I say A1. So it is A1 V1 plus A2 V2. And this is Vn Vn. That means alpha plus beta is a linear combination of V1 V2 up to Vn. This is a linear combination of, and if it is a linear combination, then this is a member of span. Therefore, alpha plus beta belongs to span. Therefore, is closed with respect to addition. Remember the definition of subspace. Subspace is non-empty subset of the vector space, and if all the properties of vector space be satisfied by this particular set W, which is a non-empty, then W is called a subspace. But you remember, we people use only these two parts because remaining properties will be inherited from the parental set, that is the vector space. Okay, so the first is, now we can see the second one. Let alpha belongs to span S. Okay. Therefore, alpha is C1 V1, C2 V2, Cn V1. Let A belongs to M, that is field, and here this is R. Set of real numbers. Okay. Again and again I am writing this. Now, what is A alpha? It will be A1 C1, A C1 of V1 plus A C2 of V2. This is A Cn of Vn. And this I write. This is a scalar, this is also a scalar. Multiplication of two scalars is again a scalar. So this will suppose I write this B1 plus B2 B2, and this is Bn Vn. This implies, because this is the linear combination of V1 V2 up to Vn, so this implies A alpha belongs to span of S. Therefore, span is closed with respect to scalar multiplication. Therefore, span S is a subspace of vector space. So this is the theorem, and this is very important. Sometimes it is asked in the examination. So you remember how to prove span of S is a subspace of the vector space. Okay.